Okay, here's what we're going to do. We want to be able to do all that stuff. Deal with all that stuff using a table. I don't know how to word that very well, but you'll understand what I mean when we do a problem. So let's try one like this. What if we've got the function y equals x times the square root of 4 minus x squared? Okay? So first thing we got to do is we got to find the domain. Okay, so let's pause for a second and think about how are we going to come up with the domain here. Any places, by the domain, we mean excluding places where we need to exclude values of x, right? So what are the two kinds of main danger zones we look for then? Say it again. Okay, but I mean, like, where would we have to exclude the value of x from the domain? There's two big things we've said about a million times. Negative. Here if we have a negative number under an even root, right? We can't do that for real numbers, and we can't divide by 0. It's not like there aren't other places that could exist, but that covers most of them, right? Most of the time, those are the two we look for. Well, we don't have a quotient here. There's no variables on the bottom, so we don't have to worry about dividing by 0, but we do have an even root, right? So then what has to be true? For our domain, what has to be true? Okay, so you're jumping way ahead. That's good. Mm-hmm. But how'd you get there? Okay, and once again you're jumping way ahead, which is great because I'm glad but you got there by saying whatever's inside has to be non-negative, right? So anything inside the radical, and this is where I'd urge you to start with this stuff, right? Let's identify where's the potential exclusionary. What's the issue that's causing us to exclude values of x? And then determine what's the condition that has to be met for values to be in the domain. Well, everything under the radicals, everything in the bubble, has to be greater than or equal to 0. It has to be non-negative, right? So essentially, we're just solving that inequality, right? Okay, so how are we going to solve that inequality? Because this is something that, these are the kinds of issues. The calculus, a lot of times, is really not the big issue that I see with people. It's how do you deal with the hard algebra, right? And we've got to put all these kind of things together. So suggestions. How can I deal with that? There's a number of ways we can do this, but I want to make sure you're comfortable dealing with a problem like that. Add x squared. We could add x squared to both sides, right? If we add x squared to both sides, I'm going to get the x squared on the other side of the inequality. So that's the same thing as saying x squared is less than or equal to 4, right? Okay, now what? So now what? Square root. Okay, I thought I heard that. It was quiet. Got bad hearing. I thought I heard that. So if we square root both sides, then that's going to, now what's that going to give us? Okay, so it gives us a plus or minus, but the plus or minus is difficult to deal with when we've got an inequality there, isn't it? Right? That's probably where people are saying, I'm a little uncomfortable with that. Right? Let's just see what would happen if we did that. If I square rooted both sides, I'd get x is less than or equal to plus or minus 2. That doesn't really work, does it? Right? You get that? If it's an equation, it's fine, right? But when it's an inequality, that doesn't, we kind of glossed over a step that led to that now becomes important. And I've mentioned this, we talked about this in Algebra 2 a couple years ago. I think we've talked about it this year, but what's the missing step there? When we square root both sides, we get the plus or minus because we skipped over an important step in this case. Well, not really. If I square root both sides, what is technically the definition of the square root of x squared? Absolute value of x, right? So there's the missing step, right? We get the absolute value of x is less than or equal to 2, okay? Because the square root of 4 is 2, right? But the square root of x squared is the absolute value of x. Now, when we're solving an equation, let's just remind ourselves why we can kind of skip through this step. If we were solving the equation x squared equals 4, when I square root both sides, and I get the absolute value of x equals 2, we automatically know that because we're only dealing with the endpoints of an interval here, that the answers are plus or minus 2, right? But really what we do is we solve an absolute value equation. So think back to Algebra 2 and pre-calculus when you solve the absolute value equations. What did you always do? There's a pattern to this, right? If you have the absolute value of something, call it u, is equal to a number c, the pattern is, right, whatever's inside, we're going to trade the absolute value inequality, or absolute value equation, for two regular equations. Remember talking about this, right? So whatever's inside is either going to equal the number, or whatever's inside is going to equal the opposite of the number. It works that way every time, though, and so we can just skip through this and say, okay, we know we're just going to get plus or minus 2. And we skip that step, right? But here it's a little bit different. Here we've got an absolute value inequality, right? So let's think back to how we deal with absolute value inequalities, right? And this is good review, it's healthy review. So if we have the absolute value of u, where u is just something, could be some expression involving x, could be 3x plus 4, who knows, something, is less than or equal to some number a, what does that translate to in terms of a compound inequality, a regular compound inequality? Once again, we're making a kind of a 1 for 2 trade. You're going to trade one absolute value inequality for 2, meaning a compound regular inequality that we know how to deal with. And think why we're doing this, because we can't do algebra with absolute value bars there, right? We always have to do something to get rid of those before we can do regular algebra, right? They really complicate things, okay? So what was that relationship? What do we do? If we have the absolute value of something is less than a number, here's how if I haven't done math in a long time, here's how I think about this. That means that the value of whatever's inside here has to be small, doesn't it? Right? Like if we had something like the absolute value of some expression is less than 10, let's say, right? Well, then whatever I plug in for x in that expression, what are answers that would work? 9 would work, right? 5 would work, 0 would work, -5 would work, -9 would work, but 20 wouldn't work, and -20 wouldn't work, right? You see what I'm saying? When we have to have small values, small positive or negative values. And so that means we've got to trap those values between the upper limit and the lower limit, right? So then, does it make sense? You probably remember this anyway. But then whatever's inside is going to get pinched in between the negative value and the positive value, right? That ringing a bell? Mm-hmm. Okay. What if we had instead the absolute value of some expression is greater than some number, like the absolute value of 2x plus 3 is greater than 10. What are values that would work? Well, any value of x that's going to make this equal to something like 20 would be fine, or 40, but not 5, right? -20 would be great because the absolute value makes it positive. -40 would be great, but -5 is not. So this time we want big positive or negative values, right? And so we end up with either what's inside has to be big and positive, or what's inside has to be big and negative, right? So where are we here? Well, this is a small value, right? Small positive or negative value issue, right? So the trade we make here is x has to be greater than or equal to -2. Let's hang on here. Less than or greater than or equal to -2, sorry, and less than or equal to +2, right? That make sense? Okay. Does that think about our problem? In the context of the problem, that works, doesn't it? X squared has to be smaller than 4, right? And we probably could have just jumped right from there without having to set this thing greater than or equal to 0. Probably you could have just jumped right to that step right there, couldn't you? Right. Okay. That make sense? Okay. All right. There's another way to look at this, but I don't think do you remember, I mean, you tell me if you want to see it. Do you remember like factoring this and looking at the signs of the factors? You might have done it last year in pre-calculus. Remember ever doing anything? I mean, you tell, I won't, if this is gonna complicate things too much to go through it, I won't do it. But you could do something, you just tell me to stop this, Roy, or don't stop. We could factor this into 2 minus x times 2 plus x. Oops. Right? You remember doing something like that? And then you just want to find the places where, what are the values where if we're going to, this whole thing has to be positive, either this has to be negative and that has to be negative, or this has to be positive and that has to be positive. Remember doing something like that? Yes or no? Raise your hand if you want to see that, or raise your hand, don't raise your hand if you think that's just going to be excessive. Yeah, I get too much information, I get you. Yeah, that's fine, that's fine. Some other day we'll look at one like that, but I just bogs us down too much today. So we got our domain, right? Okay? So we can start to make our table then. And I'm gonna go to the next page just so we can make this really clean. So the previous page was all about how to find the domain. This page is just going to be, we already know the domain, now let's do the rest of the stuff. Our domain was, right? -2 to 2 inclusive, okay? So we got domain, now we need to find a bunch of calculus stuff, so what are we going to do? Take derivatives, right? So first derivative, that's just a 1/2 power, so we got a product rule thing here, right? So let's do the square root of 4 minus x squared times the derivative of x, which is 1, right? Plus x times the derivative of the square root of 4 minus x squared. So that's a chain rule deal, right? It's a 1/2 power, so what are we going to get there? What's the square root of? Or the derivative of the square root of 4 minus x squared. Think of it this way. We could rewrite our function if we want to.
1/2.
There you go.
4 minus x squared.
I could rewrite this as that, right? If I do that, the square root is really just a 1/2 power, right? So we'll differentiate the green version. Either one is going to work. So x times the derivative of all this. Now we got to use chain rule. So the derivative of hand to the 1/2 is what?
Over 2 squared.
Okay, so yeah, 1/2 hand to the -1, too. So we get over, there's my 1/2, 1/2, times hand to the -1/2. That puts the hand on the bottom if we want to write it as a fraction, right? And then the derivative of hand would be what? -2x. Okay, everybody with me? Good luck. Give it to them. Okay, so I could cancel the 2's, that's convenient, right? And so I get y prime equals, if I want to write this as square roots, and I want you to see this, I could write this as the square root of 4 minus x squared minus x squared over the square root of 4 minus x squared. And one way I could do this would just be to get a common denominator, right? If I multiply top and bottom by the square root of 4 minus x squared, what am I going to get over here? God, why don't you put that away? I want you to watch this. Right, okay, so this first term is just gonna become, if I multiply top and bottom by the square root, the square root times the square root undoes the square root, so I'm gonna get a 4 minus x squared minus x squared over the square root of 4 minus x squared. We also, if we wanted to, we could have just written this as a negative 1/2 power and factored out 4 minus x squared to the minus 1/2. That's the way we typically did it back in chapter 2 when we were doing a bunch of this stuff, right? Okay. If I simplify this, I finally end up with y prime equals 4 minus x squared is 4 minus 2x squared over the square root of 4 minus x squared, right? Okay, so now, where are the, let's analyze this a little bit. Let's find the first derivative critical numbers. Okay, so where is our derivative equal to 0 in our domain? I don't think so. So y prime equals 0 when what equals what?
Top equals 0.
Okay, so when 2x squared equals 4,
Yeah.
everybody agree? If that whole thing equaled 4, right, I'd get 0. I could set the whole thing equal to 0 and solve, same thing. So x squared equals 2, so what's x?
Plus minus, so that's square root of 2.
Okay? So there's my first derivative critical number. Is there any place, what about where it's equal to, where it's undefined? So 2 and negative 2 would be the places that would make the bottom 0, right? Okay, but are those really going to be critical numbers? Well, they're endpoints, right? So we're going to be checking those anyway, right? Because we're trying to find the extrema of this thing, right? The maximum and the minimum. So we're going to check those endpoints anyway, right? Do you need to include them? No, you really don't, right? We really only care about interior critical numbers. Exterior, endpoint critical numbers, those are just endpoints, we check them anyway, right? Okay, so now down to the second derivative. So here's our first derivative. Now we got to use quotient rule. So quotient rule. What do I do first? First step.
Low D high.
Low D high. So I got bottom.
Times.
Okay, so hold on. So Luke, tell me, what's the derivative of the top?
Top.
Derivative of the top. So we get low D high. Say it again.
Negative.
Negative 4x, very good. Okay. Minus pi, so that's the quantity 4 minus 2x squared. D low, well, we did D low, right? D low was the derivative of, that's, well, I mean, we did it as part of our earlier differentiation. So we've already done this exercise. What is the derivative of the square root of 4 minus x squared?
1/2 minus x squared.
Okay, good, so we got times, on the bottom we got a 2, right? Times the square root of 4 minus x squared, right? We get 1/2 times hand to the minus 1/2. So there's our 1/2 hand to the minus 1/2 times
Negative 2x.
negative 2x, right? By the chain rule, there's D low. And that whole thing is all divided by
Bottom squared.
bottom squared, right? So the square root squared is just 4 minus x squared, right? So that's kind of a mess, but it looks pretty familiar to what we did on that first derivative. So this is going to give us negative 4x. How about if I multiply top and bottom by, I got to get a common denominator, right? So we multiply, let's do this first. Let's cancel the 2's. So once again, I've got a square root of 4 minus x squared. So I'm just going to multiply both top and bottom by that square root, right? And so what are we going to get there? So we're going to get from this first term, square root times square root undoes square root, right? So I've got a minus, oops. I've got my minus 4x square root times square root is gonna give me the quantity
4 minus.
4 minus x squared. Good, now we've got our minus all this stuff, right? Minus a negative becomes a plus. And I've got my x times 4 minus 2x squared over my common denominator of the square root of 4 minus x squared. That's just the numerator, right? Everybody get that? That's just this. We still haven't divided the whole thing by 4 minus x squared, right? But dividing by 4 minus x squared is the same as multiplying by what? Of course, got a question. Maybe found a mistake.
Circle the X through it or something. What was that?
Yeah, so that's, I was gonna, yeah, that was supposed to be, I was gonna circle that one. I never did it. Just so you guys can see that that minus sign goes with that minus sign, but it changed to a plus sign anyway. So let's just change it. I'll make it orange, how's that? Right, because we're subtracting all this stuff. I'm subtracting a negative, made it a positive. Okay? But we still have the issue of we're dividing the whole thing by 4 minus x squared. Dividing by something is the same as multiplying by the reciprocal, right? So we can multiply by 1 over 4 minus x squared. And that actually is going to make things quite a bit easier, right? If I've got 4 minus x squared to the 1/2, which is the square root, times 4 minus x squared to the 1, what is that? 3/2, right? If I have a base to the 1 times a base to the 1/2, I get the base. If I multiply like bases, I add the exponents, right? Base to the 1 plus 1/2. So I get on the bottom 4 minus x squared to the 3/2. On the top, I bet you things are going to be nice. If we distribute the negative 4x, we're going to get a minus 16x plus, let's even be smarter than that. We could even do some better stuff, right? We could do it this way, but let's cut a step out. What can I factor out of both of these? Yeah, technically you probably factor out a 2x, but I could factor an x out of each of those terms, couldn't I? So on the top, we're going to get an x times, so those x's are gone. If I distribute the negative 4, I'm going to get a negative 16 plus 4x squared plus, I already pulled that x out, so I've got a 4 minus 2x squared, right? I mean, I could take out a 2, but let's just combine like terms. Okay, so we end up with, let me take a picture of this. So what's all that equal to if I simplify it then? 4x squared minus 2x squared is 2x squared. Negative 16 plus 4 is minus 12 over the quantity 4 minus x squared to the 3/2. I guess I could take a 2 out too, right? Make things a little simpler. So we end up with f double prime of x equals, in factored form, which is great, 2x times x squared minus 6 divided by 4 minus x squared to the 3/2. Okay, that was a bad one. Yep, right. And would we, so we took the second derivative because we were being asked to find inflection points, right? If we weren't being asked to find inflection points, would we have done that? No. Heck to the no, right? We never would do that, right? Because we could have found the relative extrema with the first derivative test. So as you're kind of getting a feel for this, right? When we're looking at this big picture where we're trying to just analyze a function, right? To sketch a function, you really only go to that second derivative row if it's convenient to do. If it's not, if it's a bear to take that derivative, do without it. Use the first derivative test anyway, right? Only do it if you're being specifically asked for second derivative stuff, like inflection points or concavities or something like that, right? Okay? But we were here. I was being mean. So let's look at the results of this then. So where are our second derivative critical numbers? Okay, well, the second derivative is undefined when x equals plus or minus 2, which we don't care about, right? Okay, those are endpoints anyway. But where is it equal to 0? Second derivative equals 0 when x equals 0, right? Where else? Emily, so when is that factor going to equal 0? When does x squared minus 6 equal 0? When x equals... Say it again. Plus or minus, good. Plus or minus square root of 6. Excellent. Good. So we got 3 critical numbers, and those square root of 6 is less than 2, isn't it? Right? Isn't it? Oh, no, it's more than 2. So do we even care about those? No. Those aren't even in our domain. Right? So we don't have to worry about those. Okay? So we only get one second derivative critical number in our domain. And so now all we have to do is make our table. Right? So our domain went from -2 to +2, closed interval. What was our first derivative critical numbers? Plus or minus square root of 2? So we got negative radical 2, positive radical 2, and then we got a second derivative critical number at 0. Right? So if we want to find everything, what would we do then? You kill 2 birds with 1 stone here, right? Concavity, right? So we apply the second derivative test. We've got the second derivative already fully factored here. So this is going to be easy, right? So we can do f double prime of positive radical 2 is going to be what? What are the signs going to be? Positive times, do we agree? Negative? Divided by positive, right? Okay? So we get negative. So the sign there is negative. What's it going to be for negative radical 2? We get negative times negative over positive, right? For an overall sign of positive. So what's that tell us? What do we got going on here? Yeah, we got a horizontal tangent, right? And we've got a downward concavity, so it's a relative max, isn't it? Right? Over here, we've got a horizontal tangent line. We've got a positive concavity, so it's a min. And what's that? Inflection point, right? Because it's a place where the function's changing concavities. Okay? If we wanted to find absolute extrema, all we'd have to do is maybe compare the endpoints, right? Make sense? So if we wanted to anchor this thing with some points, we could plug 2 into the original function. What even was the original function? There it is. So if I plug 2 in, I'm getting 0, aren't I? Right? Okay. Or negative 2. So I get 2, 0, negative 2, 0. And then if we wanted to figure out where these are, we can plug those into. We're going to get, at 0, that whole thing goes to 0, right? So that's going to be 0, 0. At radical 2, what do I get? Square root of 2 times 4 minus square root of 2 squared is 4 minus. So I get 2, don't I? Let me see that, I get square root of 2, that's all gonna be square root of 2, right? Square root of 4 minus 2. So I'm gonna get, well, this one's gonna be positive, if I plug that, or sorry, yeah, this one's positive, whoops. And this one's negative. So I got everything I need to make a pretty good sketch there, don't I? Right? Okay. Could we have, let's just look at the symmetry stuff again. Is this function, does it have any kind of symmetry? We can test for symmetry. Not that we really need to here, but this is just something I don't want to lose sight of. I know what I ended up doing. Later on in more advanced math classes, I use symmetry a ton. So that's, if you stick with math, this is something you're not going to want to forget about.
Is that rotation symmetry?
Well, let's find out. So there's the function, right? What happens if I plug in negative x? If I plug in negative x, what do I get?
Half of x.
So I get negative x times the square root of 4 minus, what's negative x squared? X squared, right? So that equals negative f of x, right? So that's odd symmetry, right? That's rotational symmetry about the origin. And so really, we could have, if we wanted to, we could have just only done the right side and then spun it around the origin and gotten the left side, just to save a little time, right?
So that would mean it has these x and y values?
Well, it would just mean, I mean, like if we graph this thing, what do we got? There's the xy plane. We know we've got a point here. We got a point there. We got a point over at, if that's 1 and that's 2. Over at the square root of 2, we got a point that's over the square root of 2 up 2, right? And it ends at 0. So over here, and this is where we're shifting concavities, right? We're doing that. So all I got to do is just spin that thing around the x-axis, and I'm obviously just going to get that, right? We're done. Okay.
So, calculating extreme, would that be useful to say economics?
Yeah, and that's what we're going to be doing that stuff soon, right? Where we're going to go. So once we're going to practice this. We're going to practice doing a variety of different functions, and we're about out of time, aren't we? Man, it's like one problem for this. That's the way calculus is. So just looking ahead a little bit. Here's some things that we didn't get a chance to get to today. I've gone along, but we'll do after spring break. We'll get back and look at these. But we want to look at some situations where, what if our original function had been, let's say, a rational function? Then what else could we have added to our table? Well, we could have added vertical asymptotes, right, where we had unique zeros of the denominator. We could have taken limits at infinity to see where the horizontal asymptotes are, and we could have added those to our table, and I'll show you how we can do that next Monday. Take a week off, week from Monday. And we're going to get some situations, and I don't know, we talked about this in Algebra 2, but maybe you did in pre-calculus. Do you remember talking about slant asymptotes?
Yes.
Okay, we can do slant asymptotes too on the table. So there's a bunch of other cool stuff we can add to those tables that's really pretty useful. Okay? All right, let's call it a wrap. I will